Okay, in this lecture we're going to talk about logical operators, also referred to as Boolean operators. Basically, these are true and false values. There are different operators. We're going to start talking about the AND operator. The AND operator is a binary operator. That doesn't necessarily mean that it operates on binary numbers. It means that it needs two operands. If we think about addition, arithmetic addition, addition is a binary operator. That is, it takes two numbers. We usually have a plus sign and then a numeric value before the plus sign and a numeric value after the plus sign, and those two things are added together. So like 2 plus 2 would become 4. In the case of the first logical operator we're going to talk about, which is the AND operator, we will say that the expression is true if both A and B are true. So here on the sheet I have a truth table for the AND operator. There are 4 possible combinations of true and false for an AND operator. So we can have both false. The first can be false, the second can be true, the first can be true, and the second can be false, and finally what comes before and after the AND can both be true. So what we have here is a truth table. We have the possible values of A and B, and then on the right hand side we have the result of A and B. So A and B is true if A and B are true. So the only place that is true is down here at the bottom. A and B are true, so the expression is true. For all other possible combinations, we're going to end up with false. So that's the truth table for AND. Over on the right hand side, we have an example of what it might look like in computer code. So we might want to check a condition and say if x is greater than 10, and x is less than 20, then we're going to print yes. So the only time we would get yes printed is if we entered this section of code and x was somewhere greater than 10 but less than 20. So that's an example and information on the AND operator. Now then, if we move down to the bottom, we have the OR operator. So the truth table for that, again, we have the 4 same possible combinations of true and false. Both be false, first false, second true, first true, second false, and finally both A and B are true. So the expression A or B is true if A or B is true. So if we look at the first one, they're both false, but down here B is true, A is true, and in the last case they're both true. So again, the result of A or B is true if A or B is true. So another example over to the right of some basic code. If y is less than 10 or y is greater than 100, then print yes. So if we're somewhere between 10 and 100, neither of those would be true and nothing would happen. But if the value of y was less than 10 or greater than 100, then we're going to get yes printed out. The next operator we want to talk about is called exclusive OR, sometimes written XOR. Exclusive OR is, I guess, what you would call a variation on the OR operator we just talked about. In the case of exclusive OR, A exclusive OR is true if A or B is true, but not both. So slightly different. So the truth table, again, exclusive OR is a binary operator, so we would have A and B values. So we can have both false, false and true, true and false, or true and true. So like I said before, A exclusive OR is true if A is true or B is true, but not both. So in this case, we'd have false for those two values and true for the two middle rows of the truth table. An example of exclusive OR is shown over here. If A is less than 10, exclusive OR X is greater than 10 or less than 20, then print yes. So if one of those was true, that is X is greater than 10 or X is less than, we would print yes, but if both of those is true, we would not print any value. Down here at the bottom, we have the NOT operator, sometimes called the complement operator. This is a unary operator. That means it only operates on a single value. So in the case we have a single value we'll call A, there's only two possibilities, false and true. So not false is true, not true is false. So that's why it's called the complement operator, just because we basically flip those. So here's an example over here where we would input a line, and while we still have lines to read on that file number 0, we would take the length, we would print the length, and then we would input the next line. The place the NOT operator is right here in the while loop, while not end of file. So each time we check, we say, are we at the end of the file on the input file? If the answer is false, not false is true, so while loop continues while the condition is true. So we would read line after line after line from file number 0. When we did hit the end of the file, this function EOF, end of file, would say true, not true is false, and false is the condition that would terminate the while loop. So we would come down here and continue executing after, in this case, the while end on line 140. A topic related to logical operators is something called short circuit operators. In particular, we have two operators that fall in the category of short circuit operators. That is the logical and the logical OR operators. The reason these are called short circuit operators is if we look at this first line and we have a whole bunch of A's together, A or B or C or D. Here I've shown 6, but let's say this could be 1,000 values. What happens is once we go through and let's say A is false, but B is true, false or true is true, and once we have a true, there is no reason to continue. There can be as many falses or as many trues or any combination. Once we encounter that first true, we know that the result is going to be true, so there is no reason to continue evaluating this expression. So it's much more efficient. We can just stop then. So over here we have a comment that says, in the case of OR, we evaluate it left to right until a true is found. When a true is found, we can stop processing and know that the entire expression is true. Likewise, with the AND expressions, we go left to right until a false is encountered, because once you have a false, there is nothing that you can AND with false to get a true. So once a false is encountered, we know that the entire expression is going to be false, and we can just move on. Down at the bottom, what is, quote, truth? Most programming languages define false as anything that looks like 0. And things that look like 0 are an actual 0 value, an empty string, or an undefined variable. So those things are going to be evaluated as false. If the computer needs to store the false value, typically it's just going to store the value 0 in the variable. And then, now that we've defined false, we can turn around and say anything that is not false is true. So any other thing in the world would be evaluated as true if it was being evaluated in a logical context. Now, most programming languages, if they need to store a value of true in a variable, they will simply store the value 1. So a lot of times people say it's 0 and 1, but this is how most programming languages actually define those. Okay, on this sheet I have 4 examples that show you how to work through short circuit operations. So basically in the first one we have some ORs and we have a check for equivalency. So we would start at the left and we would look at the first expression, which is substituting in values for A or B. Does 1 equal 3? Well, that's false. So we need to continue on. So sometimes students have a little bit of issue with this, but the next one is 3. So is 3 true or false? Based upon the discussion we just had, it's a non-zero value, or quote, doesn't look like 0. So this is true. In the case of the OR operator, as soon as we get a true, we know that the answer of the expression is going to be true. And typically what I'll do is I'll do something like that to show that the short circuiting occurred at that location in the expression. That is, we had to look at the value B, but after we looked at the value V, we did not have to continue any further because we already knew the answer. So over here in expression 2, we have some ands. So we'll go ahead and substitute in for A and B. Is 1 less than 3? That is true. So in the case of the and, we're looking for a false. So we'll continue on. B is 3. Is 3 equal to 2? No, it's not. So that is false. At this point, since we're using the and operator, we know that the entire expression is going to be false, and the short circuiting occurred at this location. I had to evaluate B equals 2, but I did not have to go any further. If we look at example 3, we'll plug A in. Is 1 greater than 10? That is false, so we need to continue on. B is 3, so is 3 greater than 10? That is false. Finally, is 1 greater than 10? Well, that's false also. So in this case, we didn't have any efficiency. That is, we had to go through and evaluate the entire expression. And so short circuiting did not occur, but we evaluated all the different conditions and ended up with X being false. Over here in example 4, is 1 less than 3? That is true. So we need to continue on. So B is 3. Is 3 less than 3? No, it's equal to 3. So this is false. And in the case of and, we're looking for a false. So short circuiting occurred at this location, and we know that the value that will be stored in X will be false. So that's some discussion and some examples on logical values and short circuit operators.